Thank you all for your participation in this webinar. We're looking forward to sharing with you the exciting new features in version 11. Here I have on the screen my LinkedIn address. If you would like to connect with me, feel free to do so. And here is our agenda. First, we'll do an overview of what's new in SigmaXL version 11, which includes overlay histograms, interaction plots, standalone interaction plots, the fraction of design space plots, improved two-level factorial screening designs, augment two-level factorial screening designs, general full factorial designs, improved response surface designs, definitive screening designs, and optimal designs. So that'll just be a quick overview. And then we'll go into in terms of what we actually demonstrate in today's session, we'll demonstrate the overlay histograms, the interaction plots, and we'll do two examples of augment where we add axial points and we do a fold over. So in the overview of what's new, we have the overlay histograms. So this is nice. You can, especially with doing like a before and after comparison, you can nicely see the improvements. In the past, we have these on separate charts, but now they are on one chart with transparency so that you can have a nice visual comparison. And we have the interaction plots in the two-way ANOVA. We've ported it into a standalone option under Graphical Tools, interaction plots. This is a new graphical tool, fraction of design space plots. We will introduce that in more detail later on. And just to point out, it's a way that allows you to compare response surface and optimal designs. So here, for example, I'm comparing central composite, rotatable, central composite faced, and box Banken. And the 0 to 1 corresponds to the fraction of design space. So we simulate 100,000 designs, and basically it's the percentile. And then on the y-axis is your standard error of your mean or your margin of error. So it allows you to compare the predictive quality of the designs. This is a new graphical tool and is a very helpful tool to allow you to make decisions like how many replicates should I use in my response surface and what type of response surface design should I use. Here's a comparison of the different optimal designs, D-optimal and I-optimal. I-optimal is designed for low prediction error, so it shows up as the best because it has the lowest standard error of the mean. And D-optimal has other properties, desirable properties, but it's not as good as I-optimal when it comes to prediction error. And the overlay fraction of design space plot means that you are able to overlay different types of design. So you can play around with different scenarios, replications, at center points, and so on, and then you do an overlay so that you can compare the prediction ability of those various designs. We also improved the factorial screening designs. We have an expanded catalog with up to 128 design runs. You can use continuous or categorical, up to 19 continuous and or categorical factors, and you can specify, you get an aliasing of effects report, and you can specify the interaction order, the default being 2, but if you want to see, 3-way and so on, you can say, show me the alias report for whatever order you're interested in. We have augmenting of two-level factorial screening designs. That includes the fold over, which I will demonstrate today. Add center axial points, which will also be demonstrated, or you can replicate a design if you want to improve the power of the design. We also have added general full factorial design, which allows up to 10 categorical factors with up to 10 levels. And for example, one of the things that we will demonstrate in the next webinar is using one categorical factor with block-on replicates for a randomized complete block design. Response surface designs have been improved. Again, the catalog allows up to 128 design runs, cube runs. You can use up to 8 continuous factors and 10 categorical factors with 8 levels. You can choose between central composite designs with minimal, which is 2 center points, uniform precision or orthogonal blocks, and then box-Benken designs for 3 to 7 continuous factors. A new one, definitive screening designs, which I will introduce in the next webinar, next month's webinar, is a powerful 3-level screening design, and we allow up to 19 continuous and or categorical factors. Definitive screening designs are very nice because in addition to modeling main effects, you can also estimate quadratic terms. If the number of significant factors is small, say 3, then you can actually build a response surface model directly from the definitive screening design. So more on that coming up in the next webinar. Optimal designs. There are 3 types of optimality: D-optimal, I-optimal, A-optimal. We won't be getting into that in this webinar. That will come later, but just a high level, D-optimal is recommended as an efficient general purpose alternative to classical screening and 2-level factorial designs. So if you have a tight budget or the runs are very expensive, then the D-optimal gives you a good design that is typically much more efficient than you would get when you use a classical design of experiment. I-optimal is recommended for response surface designs where the focus is on minimizing the prediction variance, and A-optimal is recommended for screening design. So under optimal designs, 1 to 19 continuous and or categorical factors. You can apply linear constraints to the continuous factors, which is nice if you, for example, max temperature, max time causes furnace meltdown, then you can specify constraints so your design of experiments doesn't include those extreme conditions. And then you get a report of optimal design diagnostic metrics, model term standard error, and variance inflation factors. So you're able to then, before you actually go out and collect data, you will be able to assess the quality of the design. A power calculator has been improved with detailed power information that I will be demonstrating today. Fraction of design space plots, you'll get an introduction to that today and more on that in the next webinar. And option for randomized or equally spaced center points, I'll be demonstrating that as well. You can randomize runs with a seed as clock or specified value. And we tie the analysis DOE to advanced multiple regression, so you can use stepwise, best subsets, and multiple response optimization. Okay, so that's the high-level overview. So now what I want to do is I want to actually get in and start demonstrating the tools. We're going to start with the overlay histograms, and this PowerPoint will be available. I also want to mention that everything that we're doing here is in the SigmaXL workbook, so you can go through the workbook and reproduce what we're doing here, or you can use the PowerPoint slides if you want to review any of this content. So first I'll go to SigmaXL. This is the familiar customer data where we have overall satisfaction on a 1 to 5 scale, where 1 is very dissatisfied and 5 is very satisfied. We have customer types 1, 2, and 3. And we want to do a histogram of overall satisfaction versus customer type. So I go to Graphical Tools, and this is the overlay histograms and descriptive statistics that we're going to demonstrate, the new feature. So we go overall satisfaction by customer type, and we click OK. And this is our overlay histogram. So you can see customer type 1, customer type 2, and customer type 3. Now the nice thing is, if you want to change the colors, you can separate the charts. You can go into your Excel options. You can change the transparency level if you wish, or if you want to change the colors, and then after you do that, you just recombine the charts. So that's a nice visual comparison. Now, we actually allow up to 5 group categories, but we really recommend 2 or at the most 3, because the chart just gets too messy if you have too many groups, and ideally really comparing 2 things. So that's where we have the before and after improvement. So I have catapult data, before and after improvement, and I want to do an overlay histogram of that. I'll go Graphical Tools, overlay histograms, and we'll do distance by before and after. So there were improvements that were made. So the before is here in catapult distance, and then the after, you can see dramatic reduction in variation. And again, you can separate and combine the charts. Plus, you get your descriptive statistics. Okay, so that's a new graphical tool, the overlay histogram. The other graphical tool that we added are the interaction plots, standalone interaction plots. And we'll demonstrate that. So we'll go to Graphical Tools, interaction plot. This is the same plot that you would get if you were to run a two-way ANOVA. We'll do overall satisfaction by customer type and size of customer. In the actual slides, I have average number of orders per month, but we'll stay with overall satisfaction. And so here you can see in the interaction plot that the satisfaction score depends on customer type, and the impact that customer type has on satisfaction depends on the size. And you can see here with the changing slopes, again, the impact or the effect that size of customer has on satisfaction depends on the customer type. So you kind of two different camera angles for your interaction plot. So that's the interaction plot. As I mentioned, that was in two-way ANOVA, and it is the mean values, the plot points are fitted means, not data means, which doesn't make a difference if the data are balanced, but if the data are unbalanced, just be aware that these are fitted means. So that's the interaction plot. And we're now ready to demonstrate the first augment. And I'm going to switch over back to the PowerPoint to introduce this. So we're going to illustrate the use of advanced two-level factorial screening design with the factorial plus center point portion of an RSM design that was that's in the workbook under Part D, Design and Analysis of a Response Surface Experiment. So basically what we've done is we've split it out to demonstrate the adaxial. So first, the factorial and center points for the cake bake, and then we will augment that with axial points. So the response is taste score on a scale of 1 to 7, where 1 is awful and 7 is delicious. Average scores for a panel of tasters have been recorded. The continuous factors are bake time, 20 to 40 minutes, and oven temperature, 350 to 400 Fahrenheit. The experiment goal is to find the settings that maximize taste score, and then after the analysis, the design will be augmented to add axial points to make it a response surface design. So now I'll go back into SigmaXL, and we'll switch to, actually let me just start with a blank workbook. So to do this, we go to SigmaXL, Design of Experiments, and this is the Advanced Design of Experiments options. All right, so the basic DOE nothing has changed there. So all the new features in version 11 come under Design of Experiments, Advanced Design of Experiments. And so for this exercise, we're going to start with a two-level factorial screening design. And that comes up with number of continuous factors. Well, we have 2, time and temperature. Number of categorical factors is 0. The design that we're going to select, initially, it's just a full run to the 2 full factorial. And we'll just go with the defaults here. Number of replicates, 1. Number of blocks, 1. Number of center points per block, 0. And I want to start with the design power information. Given the default, what we see here is that we have very low power to detect an effect of 3 standard deviations. Okay, that's a large effect size. And you have to go all the way to 6 standard deviations to get just to get to medium power. So what that tells us is that this design is underpowered. We really need to add replicates. If you scroll down, you get additional information. The error degrees of freedom to estimate power is 2. You have options here. You can say, I want to consider power for one main effect or all main effects. When you do that, however, that actually reduces the error degrees of freedom. And if you add main effect plus two-way interactions, you get a message saying power cannot be calculated when there are no degrees of freedom for error. All right, so we'll go back to one main effect. And so what I'm going to do now is I'm going to replicate I'm going to make it 2 replicates. I'm going to put them in 2 blocks, and I want 2 center points per block. This actually was to match the previous experiment that we had in the workbook, the factorial portion of the response surface design for the cake bake. So now we can go to all main effects, and we still have lots of degrees of freedom for power. And when we do that, we see that we have medium power for a 2.5 standard deviation effect, an effect size of 2.5 standard deviations. Okay, so not ideal, but certainly better than what we had with only a single replicate. And what I'll do now is I'll type in the factors. So this is bake time. Bake time. And bake time is 20 to 40. And then we have oven temperature. And oven temperature is 350 to 400. The response is taste score. I'm going to randomize the runs, but I'm going to uncheck randomize center points. And when I do that, what's going to happen is that the center points will be equally spaced within a block. So that's a nice feature. It's optional. Basically, if you want your center point at the start and at the end, or at the start, middle, and end, you just uncheck randomize center points. If you don't want that, if you want it fully randomized, then you just check randomize center points. We also have the ability to specify the seed. So that's useful, for example, in a demonstration or following the workbook. That way the runs are identical. When you produce a design, everything matches what you're doing. Following the workbook will match what you have on your screen. And we'll go ahead and click OK. And this is our experiment. As you can see, the center points at the start and end of each block. The runs are randomized within the block. The blocks are also randomized. And then here's our report. There is no aliasing of effects. Remember, it was a full factorial, 2-factor full factorial. Here's the power that we saw, medium power for 2.5 standard deviations. And so that all that information comes up. So now what we want to do is we want to open up the file where the taste scores have been, where the experiment was carried out and the taste score is entered. So for that, I have the file cake bake, advanced 2-level factorial example cake bake. And this has the taste score values. And so we're now ready to analyze the data. So we go to design of experiments, 2-level factorial, and we go to analyze. The taste score is the response, and we're going to specify main effect plus 2-way interactions. It is a full factorial, so we can estimate main effects plus interactions. What I'm going to do is I'm going to uncheck include center points, because I want to clearly demonstrate to you why we need to add axial points. And in order to see that, we don't want center points in the model. Otherwise, it would mask the curvature. So we'll go ahead with that. I'll click OK. And as you can see, the R-square values are quite low. So you have R-square of 66, R-square predicted of 14.6. With the exception of bake time, most of the terms are not significant. And you can see here, error, a lack of fit is significant. And then if we look at the residuals, you can see here strong curvature in the residuals. All right, that's with the center points removed from the model. Now, if I go back and I refit and I add center points, now my model looks really good. My R-square values are high. Everything is significant except for the blocks. I no longer have a lack of fit. However, the problem is that this center point term is significant. And that means that there is curvature. There is at least one quadratic term. But unfortunately, we really can't use this model to make predictions as is, because effectively the quadratic terms are aliased. So just because you have a good model as far as R-square goes, as far as the p-values go, you really don't have anything here that you can use from a prediction point of view. And so the only way you get that is you have to add axial points. You have to turn this into a response surface design, which allows you to model the time squared and the temperature squared term. Okay, so that's what we'll do now. And to do that, I will go back to the cake bake example, and I will go design of experiments, augment design. You have the choices of fold over, add center axials, and replicate. We will choose add center axials. I'm going to uncheck add center points because we already have center points. We could include them, but what we want is the final design to look like the previous example that we had in the workbook. We're going to specify 2 replicates of axial points so that it matches the replicates in the factorial portion. We want face centered, again, to match the previous cake bake design. I'm going to turn on fraction of design space plots, and I'm going to set the seed to a value of 1, 2. All right, so this will now create a design that adds the axial points to the design, which will allow me to estimate the quadratic terms. So these are the axial points that have been added. These are in random order. And this is how we would want to carry them out in an actual experiment. So we'd go out, we'd collect the data with the fraction of design space plot. And again, we're gonna be demonstrating this as a separate item. But I showed you how the power analysis has been improved. The FDS, or fraction of design space plot, is a very nice tool to allow you to assess the quality of your response surface design. And you can look at either the standard error of the mean or the margin of error. And as I mentioned, we basically simulate 100,000 designs, and then this fraction of design space is what percentage of the design space gives you what standard error of the mean. So I have here the 95th percentile for the margin of error is 1.086. All right. Now, to get the taste score, I multiply that number by the model standard error. So if I go back, the model standard error was 0.14. So I multiply a 1.086 number times 0.138. That gives me 0.15. So that's going to be my margin of error. And by the way, I haven't collected any data as far as the response surface portion goes. So just like you can do power before you collect data, here the fraction of design space plot gives you information about your design before you actually have gone out and collected data. And that way you can determine if you need to add more replicates, for example. So here we have a margin of error of 0.15. This is actually at a 95% confidence level. So 95% of the designs are with a 95% confidence interval gives me a margin of error of 0.15. So given that the T-score is on a 1 to 7 scale, this is actually a reasonably good margin of error for prediction. Okay, so that's just very quick. We're going to come back. We'll demonstrate the FDS plot in greater detail. This is just kind of an introduction or high-level introduction to this graphical tool. Very nice graphical tool. What the power is to a factorial design, fraction of design space is to a response surface design. So now we're ready to actually analyze the data. We went out, we collected the data, and I have my cake bake axial augment populated. And so I'm going to go SigmaXL, design of experiments, augment, analyze augmented design. By the way, if you accidentally pick the wrong analyze menu, SigmaXL will detect that and take you into the right place anyways. All right, so that's just for your information. We can select T-score, and the default is a quadratic model, and we're going to select all the terms. We can show the main effects plots, interaction plots, display regression equation with uncoded coefficients, and all right, so let's go ahead. Remember, we did the design first as a factorial. We discovered that there was significant curvature, significant lack of fit. We went out, we added our axial points, we collected the data, and we are now ready to analyze this as a response surface design. So we see here our R-squares are high, much like we got with the added center point, but the difference now is that we are able to model the quadratic terms, so the bake time squared and the oven temperature squared. So it's a proper response surface design now. If we come over here, we see this is the actual prediction equation. And you can type in numbers. So I'll type in, for example, 23 and 368. This gives you a predicted T-score of 7.05. And you have your standard error. Let's get this over. You have your lower 95% confidence and your upper 95% confidence interval. So the margin of error is actually this number, 7.21, minus this number, which is 0.16. So if I just say equals this number minus the predicted response, that's the 0.16. And that's pretty close to what we obtained in our fraction of design space plot. So the FDS plot is predicting what your margin of error is going to be before you actually collect any data. All right, so this is a good number given the fact that we're on a 1 to 7 scale. A margin of error of 0.16 is acceptable. And we're going to run optimize, so change the goal from target to maximize. We'll run the optimizer, and then we'll paste the values. And there's our predicted response for our optimal. We can do contour surface plots. So again, this is our sweet spot here in terms of bake time and oven temperature for maximum. Okay, this is, of course, we had this in the advanced multiple regression tools, but this is now, we've integrated the design of experiments with the advanced multiple regression tools. And in addition to the single response optimizer, you have multiple response optimization as well. I won't be demonstrating MRO here though. You have your main effects plots. You have that curvature because there are quadratic terms, so it's a little bit different from the usual main effects plots. Your residuals look pretty good, no obvious patterns. Okay, so that's what I wanted to demo from the cake bake perspective for the adding of the axial points to turn factorial design into a response surface design. Now we're going to do a fold over augment. And let me go back to the PowerPoint. So this fold over design is a famous example from Box Hunter and Hunter. Design of Experiments, Statistics for Experimenters textbook. And in that book, they describe a 7-factor, 8-run, 2 to the 7 minus 4 bicycle hill climb experiment. The response variable is the time that it took to climb a hill in seconds. The runs were made in random order, but will be given here in standard order to match the book. 7 categorical factors are used: seat position, up, down, dynamo, off, on, position of handlebars, up, down, gear setting, low, medium, wearing a raincoat, on, off, had breakfast in the morning, yes, no, tires, hard, soft. So it is a 7-factor, 8-run experiment, fractional factorial design, and that's what we're going to start with. So again, we'll switch over, and I'll start off with a blank worksheet, and we'll go SigmaXL, design of experiments, 2-level factorial screening designs. And in this particular case, we have 7 categorical factors. So I'll change that to 7, and we'll get rid of we don't have any continuous factors. They're all categorical. The default design is an 8-run, 2 to the 7 minus 4, resolution 3 design. So this is straight out of the textbook. The default power information cannot be calculated because there are no degrees of freedom for error. So if you change the terms in the model to one main effect, you are now able to look at power. And that's by changing the design power information allows you now to look at power. And we can see that we have medium power to detect a 2.5 standard an effect size of 2.5 standard deviations. I'm going to uncheck randomized runs so that it'll just show up in standard order. And to save time, I'm not going to populate the various factor names because we actually already have that worked out, and that's what we'll be opening up a completed worksheet. But you would typically fill out all this information, the low and high settings, and the same with the response name. So I will click OK. This gives you your design. This shows you the aliasing of the effects. All right, again, because it's a resolution 3 design, we can see that main effects are aliased with two-way interactions. Actually, I'm going to open up the file that we're going to use, which is BHH bicycle, and that's with the populated. So when you actually type in the factor names, you get a legend. So A is equal to seat, B is equal to dynamo, C equals handlebars, etc. And then you have your design generators, you have your aliasing effects to order 2, and you have your design power information all given to you. And of course, the assumption here is that the interaction terms are insignificant relative to the main effects. Whenever you're doing a screening design like this, that is an assumption that you're making. So we're going to go ahead and we're going to analyze this. We have our times in seconds for the hill climb. SigmaXL, design of experiments, screening, analyze. We'll do the time. We'll select all for the selected model terms. I'm going to uncheck residual plots because there are 7 coefficients plus the constant in 8 runs, so there are no degrees of freedom to estimate residuals. And we can do main effects plots. And then we'll click OK. And this gives us our analysis. Now you'll notice that there are p-values. Even though I said it was a saturated design, the p-values are based on lengths pseudostandard error. So when you have a factorial design, a 2-level factorial design that is saturated, the number of terms plus the constant equal to the number of runs, you can use lengths pseudostandard error to get estimates of these p-values. All right, so we see that seat, dynamo, and gear are significant. We can also look at the Pareto charts. These are the standardized effects. And these are the term R square values. So again, you have D is gear, B is dynamo, and A is seat. So A is just kind of borderline. Now, what we could do here is we could refit this model. We could remove the insignificant terms and refit, or we could do forward stepwise best subsets, but we're not going to do that here. We'll do that in the next example. What we're going to do is we're going to look at main effects plots. So with the main effects plots, we can see gear going from low to high. We'll go from 55 seconds on average to 77.75 seconds. So gear adds 22.5 seconds to our hill climb time. We have dynamo off is 60.5, on is 72.5, so dynamo adds 12 seconds. Dynamo and gear are the two dominant factors. So in the book, given that gear was the dominant factor, a fold-over design was carried out. And the fold-over design was just on the gear factor. So we're going to do that. So we're going to go back here to this, and we're going to do design of experiments. We're basically just following what they do in the book. We're going to augment this design, fold over. You can select all your terms, or in this case, we just want to fold over on one term. And uncheck randomized folded runs, and I'll go ahead and do that. And this gives me, as a new block, I have 8 new runs. This is a fold over. So basically, gear, what's here is medium. The first run now is low. What's here is low. Then becomes medium, low, becomes medium, and so on. It's basically a sign change for gear. Everything else remains the same. And I have a slide that discusses what's going on with fold over. So just to kind of describe what's going on. So in a fold over design, the signs of the selected factors are reversed. So high becomes low and low becomes high, and the new runs are augmented to the original design as a block. If the original design is resolution 3 and all factors are selected, the augmented design will be resolution 4. So that means that your main effects will be free and clear of two-way interactions. However, if only one factor is selected, the new design will have that main effect free of any aliasing with two-way interactions. And the two-way interactions involving that factor will be free of aliasing with other two-way interactions. So it's effectively a hybrid resolution 3 and resolution 5. Okay, so this is what we've done here, a single fold over with the gear. Just a note here, if you have resolution 4, you really shouldn't use fold over. That doesn't really buy you anything. So that's just a comment. Now, if I'll go back. So I'm going to get the data now. So we'll open up the fold over design with the data. And we go bicycle 2. All right. So this is the data from the BHH example. We have now the fold over design. So now what we're going to do is we're going to analyze the augmented design. So we're going to do augment, analyze augmented design, time. I'll select all the model terms. Actually, I want to be able to estimate two-way interactions now, because I can do that for terms that include gear. Okay, so that's the nice thing. So I'll select all the main effects, and those interactions that include gear can be estimated because of the fold over. So gear times raincoat, gear times breakfast, gear times tires. Right, so I now have dynamo times gear, seat times gear. Get that in there as well. And and then actually, because the design, I could actually include seat times dynamo, because by including that, this is actually an alias, but I can at least include it in the model to see if it matters. I don't expect it will, but we can just include it in because we have that available to us, even though that is an alias term. All right, so that's 14 terms. Actually, I'll include the blocks in the model. I'll uncheck residual plots. And here we go. So we basically see now that this is actually very similar to what we originally obtained, but now that we have decoupled all the interaction terms related to gear, we can see that none of them are significant. Again, this is using length pseudostandard error because a saturated model. But what I'm going to do now is I'm actually going to analyze this using stepwise regression. I'm going to actually recall SigmaXL dialog, and I'm going to go into advanced options, and we'll do stepwise, and we'll do forward Akaike's information criteria. So this will run the analysis. And after doing that, we're left with dynamo and gear. Okay, so that is basically like a confirmation of what we already expected, but having done the fold over, we eliminated any concerns about interactions with the gear. I should also point out to you that in the augmented design, that the aliasing, that you can see here that gear is standalone and all the interaction terms involving gear are standalone. Okay, there's no aliasing going on, but the other terms are still aliased. Main effects are aliased with two-way interactions. If you wanted resolution 4, you could have done a fold over on all the terms. So it's up to you how you want to do your fold over. Now, having done that with the final model, I can now run optimization. So I want to actually minimize my time. So I'm going to hit minimize and run optimize. So yeah, so basically dynamo off and gear low gives me my predicted response of 49.8 seconds. Because these are categorical factors, you don't get a contour plot. But by doing the fold over, we were able to come up with a good model, final model, dynamo and gear, and we know what we have to do in order to minimize our hill climb time. All right, so that basically matches the example that was given in the book. And that actually concludes my presentation for today on the new features.
Okay, well, this concludes the first of our three-part series on the new features of SigmaXL version 11. I hope you found this session useful and informative. We strongly encourage you to continue exploring all the features within SigmaXL and to reach out with any questions or feedback via email, chat, ticket. Your insights are vital, and we strive to improve and evolve. The PowerPoint, as John mentioned, and the example data sets used in today's webinar will be available for download on our website. And the recording of our webinar will also be available for download within the coming weeks. Thank you so much, everyone, for joining us today. We look forward to seeing you in future webinars. Have yourself a great day.
Thank you.